Hi, I'm Jason Martinez from Wolfram Alpha, and I'll be presenting on how to manipulate units, physical quantities, and equations in the Wolfram language. I'm Jason Martinez. I'll be talking to you about manipulating units, physical quantities, and equations in the Wolfram language. All right, so the Wolfram language contains thousands of units, over 25,000 units. That includes things like feet and ohms and moles, as well as compound units, meters per second, that sort of thing. And it also handles over 3,000 physical quantities. These are the things that those units are measuring. And we're in the process of making those physical quantities compliant with the ISO 80,000. And you should be seeing some of that in the conference build. And we hope by the release of 12 that we'll have all of that in there. And we also have a wide range of functions continuing to add to for manipulating these quantities and physical quantities. So just a quick overview. Hopefully this isn't too small for anyone. A little bit bigger? All right. Let's see, where's the, oh, there it is. So you can make quantities just magnitude and a unit, so 1 Kelvin's difference. And we have some nice formatting for all of those in terms of their typical abbreviations. You can use natural language parsing to get your quantities. And there's a similar framework for quantity variable. So there's a identifier, so in this case M, and a physical quantity mass. If you don't include an identifier, we'll just use the physical quantity itself as that symbol. And natural language processing here is really nice because you can find the standard names pretty quickly. So if you wanted to find current, for instance, you didn't know it was electric current, you can just do control equals and quickly get that as a quantity variable. And then go and add whatever symbol you want. We also have included a lot of ways for you to specify your own units and physical quantities. So we have independent units and physical quantities. I feel like, yeah, okay. So you can say that you have some physical quantity of widgets. And so we can use that as a quantity variable. It'll format nicely. You could use it in our other functions. You can find the canonical unit of widgets, which will be an independent unit. You could use that in turn in a quantity and then manipulate things. So you could divide widgets by widgets over time and find how long it took to make 5 widgets. And you can also find their unit dimensions, which I'll talk a bit more in a little bit. But we also have a lot of functions for translating between quantity variables and quantities and these unit dimension lists. So how do we do that? So the easy parts are just getting the parts. So finding the magnitude of a quantity, the unit. We have dedicated functions, quantity magnitude, quantity unit. We can do the same thing for physical quantities. In that case, we're talking about the identifier, what that quantity variable looks like. The V here, which could be a string, it could be a subscripted expression, could be whatever you want. And you can also get the physical quantity straightforwardly. Where things get interesting is when we want to look at getting more information. So unit dimension lists are lists of ordered dimension pairs where the first item is a unit dimension, so something like mass or length or money. And the second number is the degree to which that unit or physical quantity has in that dimension. So calories, for instance, has dimensions of length, mass, and time because it's energy. It has length squared, mass to the first power, time to the -2. And more straightforwardly, perhaps, Kelvin's difference over miles has unit dimensions of -1 length units and 1 temperature difference unit. And we can do the same thing for physical quantities, but the function in this case is has a little bit more power than unit dimensions. Unit dimension works on quantities and units. Quantity variable dimensions works on both quantity variables, but also expressions that include quantity variables. So if we wanted to find the quantity variable dimensions of mass times a quantity, speed of light squared, we can do that. Again, we have energy there. And we can do things like a derivative. So here we have some function that has dimensions of radiant flux density, or a physical quantity of radiant flux density, and it's a function of time. So if we just skip ahead here, we can see what those unit dimensions are. And so if we expect that if we take the quantity variable dimensions of that expression, we should get the same thing, but one lower in time, which is the case. And this will work on much more complex expressions too. Now, this next example, unfortunately, will not work on my laptop, but it will work on the conference build. It is in version 12, and that is a quantity variable canonical unit. So that works, that finds the canonical unit for a quantity variable. And in version 12, that will work on the exact same things as quantity variable dimensions. So you'll be able to extract, do combinations of quantity variables and also derivatives. In that case, we'll be looking at what the, so for this example here, we'd be finding the canonical unit for pressure and dividing it by seconds. So Pascal squared divided by seconds. Or in this case, it would be pascals divided by the canonical unit for altitude, which I believe is meters, yes. Now, I didn't highlight it here, but you can also get from unit dimension lists to units as well. So you have to make use of a hidden way for defining your quantity variables. So you can define them in terms of unit dimension lists. So here we're saying our physical quantity is basically, has dimensions of length to the -3/2 and time to the -1. And everything will work just fine with that, including canonical unit. And in that case, it will construct a canonical unit in terms of meters and seconds. So the base SI units. So that leaves us with the missing piece. How do we get from units back to dimensions? Because we can do to physical quantities. How do we get, because we can do physical quantities to units, how do we get back again? And that's the function that we're in the process of developing, which we're calling physical quantity lookup. So that will take a quantity or a unit or a combination of those and return a list of physical quantities. Because every unit's going to correspond to a number of different physical quantities. Feet applies to altitude and width and distance and so forth. This is not necessarily how it's going to be ordered in the list. We're still discussing that. It may be that we will weight it towards what's more frequently asked about. But if you have a strong opinion on that, please let us know. But we will have a second argument for limiting this to, should be an option. Alphabetical versus popular, or? Mm-hmm. All right. Yeah. Well, I mean, I think that may be a good idea. I will look into that. All right, so moving along. And so this will work on combinations as well, an example down there. And it also, of course, work with unit dimension lists because that lets us complete this diagram. And it'll work with independent units, though in that case, we'll probably have to construct some combination of physical quantities to return something that actually matches a physical quantity. All right, so let's move on to manipulating these expressions along unit dimensions. So the first of the two functions I want to talk about here is dimensional combinations. So this is a function that takes a list of physical quantities, or quantity variables, and constructs the combination of those that yields a dimensionless expression. So we know Ohm's law, so so you can see that that expression there is going to have no dimension overall. You can also include a second argument. So here we have energy squared times the electric potential difference divided by mass, and we have all these other parameters, and we get an expression that will match the dimensions of this second argument. You can also include your own include quantities. So perhaps you have some physical constants that are important in whatever you're looking at. And so this is a way for sort of figuring out what expressions will match other things. So if you're trying to find something that balances your equation, you can find some options in dimensional combination. You can also find, of course, dimensionless numbers, which are a useful way to characterize systems without having to concern yourself with whatever units that other people may be looking at. So here's an example where we take a few parameters of interest to fluid mechanics, so things like surface tension, density, speed, that sort of thing, as well as some known dimensionless numbers that we can get from FormulaData. And we can put in these quantity variables into dimensional combinations. And it gets us a long list. But we can also see, we can also see how we could construct these already discovered dimensionless numbers from those dimensional combinations. And in almost all the cases, it's just simply taking one of those solutions to a power. So Archimedes number is the 8th solution from our list to the 3rd power. There's one solution, the Brownell-Kantz number, where we take the 3rd solution, this one, and the 13th solution somewhere down here, squared, and that gets us our dimensionless number. And we could apply this to all sorts of things. Recently, last year, there was a paper in the field of economics looking at dimensionless price impact functions. So they had a number of physical quantities that they had constructed. Stock price, which is money per share, bet size, trading volume, stock volatility, bet cost. And so they took these, found a dimensional combination that worked, and were able to analyze that. So let's just generate that number. So if we don't specify that we don't want generated parameters none, it'll give us a general solution for the dimensional combinations. Any value of C1 or C2 that we put up here will yield a dimensionless expression. But if we specify generated parameters none, we'll get the lowest order solutions. And we can see that we can construct the expressions they got out of these general solutions. So this is just the reciprocal of their first expression is the reciprocal of that 3rd solution with the cubic root. And their second expression is just that combined with the first solution. Now the other function that we have for dealing with transforming expressions is non-dimensionalization transform. And this lets you transform an equation by removing any dimensions from the quantity variables within that equation. So here we have a quantum harmonic oscillator equation. And we have a whole host of quantity variables. But once we non-dimensionalize it, we'll only have 2 at the end. So we're going to specify the 2 that we want at the end. We have psi and our x here. And we also specify what the symbols we want to have in our final solution. If we didn't specify that, it would still solve it. It would just create its own generated parameters to fill the gaps. And we can also get the rules that get us from the original equation to this equation There are other arguments for getting the reverse of those rules and what the various factors involved are. And another nice feature of non-dimensionalization transform is that we've also included natural units. So this is the case where the physicist says that we're going to treat h bar and c equal to 1. So we can use this to make our final expressions that much more clear. So here we're going to pull formula from FormulaData for the surface gravity of a charged spinning black hole. And we feed that into non-dimensionalization transform. And we get an expression which doesn't have any quantity variables, but it does have this ugly scaling factor there. But if we specify that we want our results in de Sitter units, which seems appropriate involving black holes, then we get this in terms of the cosmological constant. And we can compare how these natural units work on different formulas. Here's just a simple example looking at Coulomb's law and the law of gravitation, looking just at the forces involved. And we apply these to the different, the natural units to the different equations. And we can see how they compare. Some remove the factors involved entirely. Others yield some numerical number that then has to be accounted for. And that's because different units are optimized for different fields. We tried to get a fairly comprehensive list of natural units to incorporate into non-dimensionalization transform. All right, so where else are we using physical quantities and units? There's, of course, plots and solve that we're working on, getting better and better usage of. But there's also a lot of entity domains. So one of them is physical constants. This has, we introduced this late last year, and it contains over 200 constants from physics and chemistry and so forth, and provides information on those constants, things like the speed of light or the electric constant. And so you can look at different properties of them, what their names are, and their values, how certain we are about them. And we can also look at different sets of physical constants in terms of the physical quantities involved, mass or energy, or the field, so astronomical constants or cosmological constants. And you can convert these entities into quantities that you can then use, or the reverse. So this is useful if you want to look at what the numbers inside your equations mean. We also, of course, have FormulaData. I'm going to talk a little bit more about things coming in FormulaData in a moment. Here's a little hidden thing that should work in your conference build, and I think maybe 11.3. Let me see. Yes. But we'll be documenting soon. It's just bringing it into alignment with the rest of the language in supporting association. There are other domains that are making use of quantity variable, such as the physical systems, which contains all sorts of systems like various quantum systems, we have the van der Waals gas equations, and so forth. Another example here is, whoops, went too far. Measurement devices. So this is a domain that describes or contains data on a wide range of measuring devices, their range of applicability, their relation to other measuring devices, and you can query them based on their physical quantities. Oops. And the other thing that's coming, which got mentioned earlier in the week, is the formula repository. So this is a website where people will be able to submit their formulas to be added. At the moment, it is consisting mostly of formulas that we already have in the language, but we're trying to incorporate information on different physical quantities. And it'll provide descriptions of the formulas, examples using them, meta information where available about who created them and when. There we go. And with the introduction of the function repository, we'll be also expanding that to make use of that repository so that we can tackle within FormulaData more interesting cases like very complicated empirical formulas or formulas that are not just algebraic but actually have some differential component. And also coming up, there'll be just a minor footnote here of known physical quantity queue, which will allow you to check physical quantities, make sure that they're valid. And we also want to make sure get either get UnitConvert to work with natural units or create its own another function that allow you to translate quantities into natural units. So you can see how, for example, what is the mass of a whale in Planck units or something of that sort, or maybe more usefully, different subatomic particles. And that brings me to the end. I'll take any questions.